For my design project, I chose the task of creating a circuit that would simulate a dimmable light system with backup power in case of power failure. I used in my circuit a battery, a resistor, a switch, a capacitor, an LED, and a potentiometer. For the analysis of my circuit, I used KVL at node A, as seen in this diagram. I found the KCL equation at node A. I then applied NVA to that. I used the variable of REQ1 to simplify these calculations. I then solved the differential equation, and knowing that the voltage at node A at time 0 would be 0, I found C1, which led me to the equation for the voltage at node A at any time when the switch was closed. I then used Ohm's law to find the current running through the LED at any time when the switch was closed, and then I used voltage division to find the voltage potential across the LED at any time when the switch was closed. I used the equation for an RLC circuit to find the voltage at A at any time. I then used REQ2 as a variable in this equation. The voltage supplied by a battery source would be 0 for this circuit. So the final equation for the voltage at A at any time when the switch was opened is V naught E to the negative T over REQ2 times C. Similarly as before, I use Ohm's law to find the current running through the LED at any time, and I use voltage division to find the voltage potential across the LED. For my verification of my analysis, I used a combination of KVL and KCL. This led me to the same equation for the voltage at A when the switch was closed, which would then lead me to the same equations for the current across running through the LED and the voltage across the LED. When the switch was opened, I again used a combination of KVL and KCL to find the same equation as before for the voltage at any time t once the switch has been opened at node A. Then constructed my circuit. Once the switch was turned on, current would run to the LED, lighting it up. The potentiometer would then be able to dim the LED and then also make it more bright. And then when the switch was turned off, the capacitor would release its charge and the LED would stay on for a brief longer period. For my testing, I found the values of the voltage in the batteries as well as the resistance across the LED. I then, for my potentiometer, for the value of A, I use a value where it would be the least resistance of current going to the LED, and the values for R1, RP, and C were fixed. Plugging these values into my equations, I got an expected values for the current of the LED and the voltage potential across the LED when the capacitor was fully charged and the switch was closed. The current was expected to be 55 milliamps and the voltage was expected to be 1.38 volts. I then tested this for the voltage and the current. and my results were that the actual voltage and current were a bit different than the predicted values. This could have been because I did not know the exact value of A for the potentiometer or the exact value of the resistance of my LED.